This online tutorial is about leveling effect of amphiprotic solvents. Different branched acids and bases have different branched acidities and basicities. Therefore, it's not surprising to see that different branched acids and bases act and behave differently in amphiprotic solvents. However, in an amphiprotic solvent, all branched acids whose branched acidity exceeds a certain value appear equally acidic or appear to have equal acidities. This is due to the complete transfer of H classes to molecules of amphiprotic solvent from all branched acids which are stronger than the conjugate acid of the solvent. The only acid, the species that act as proton donor in all such solutions is the conjugate acid of the amphiprotic solvent. It is the Lionium cation of the solvent. On the other hand, in the case of bases, in an amphiprotic solvent, all bases whose branched basicity exceeds a certain value appear equally basic or appear to have equal basicities. This is due to the complete transfer of H classes from molecules of amphiprotic solvent to dissolved branched bases which are stronger than the conjugate base of the amphiprotic solvent. The only base, the species that act as proton acceptor in all such solutions present to any significant extent is the Li8 anion of the solvent or the conjugate base of the solvent. Leveling effect of a solvent is this tendency of a solvent to make all branched acids stronger than the conjugate acid of the solvent appear equally acidic. In the case of acids and in the case of bases, to make all branched bases which are stronger than the conjugate base of the amphiprotic solvent appear equally basic. In other words, the leveling effect of an amphiprotic solvent is its tendency to have equal acidities at same concentrations for solutions of all branched acids which are stronger than the conjugate acid of the solvent in the case of acids, and to have equal basicities at same concentrations for solutions of all branched bases which are stronger than the conjugate base of the solvent in the case of bases. In other words, branched acids stronger than the conjugate acid of the amphiprotic solvent are leveled with the conjugate acid of the solvent in amphiprotic solvents. On the other hand, branched bases which are stronger than the conjugate base of the solvent are leveled with the conjugate base of the solvent in the solutions of the amphiprotic solvent. This is called the leveling effect of the amphiprotic solvent. Let's consider some examples. We have the following order of branched acidities in aqueous solutions. In aqueous solutions, hydroiodic acid, hydrobromic acid, hydrochloric acid are stronger than hydronium cation, the conjugate acid of the solvent water. Water as a leveling solvent makes their acidities to appear the same. In other words, aqueous solutions of these acids, which are stronger than the conjugate acid of the solvent, at same concentrations have equal acidities. This is not the case with these acids, hydrofluoric acid and ammonium cation, which are weaker than the conjugate acid of the solvent. Water as the solvent doesn't make these acids appear equally acidic, or aqueous solutions of these acids don't have equal acidities at same concentrations. Water is considered as a leveling solvent for these acids, while water differentiates between acidities of these acids, so water is considered as a differentiating solvent for these acids. Here, consideration of dissociation reaction and acidity constants are very useful. For the branched acid HA, in aqueous solutions, the acid dissociation reaction is as follows. The equilibrium constant of this reaction is the acidity constant of the branched acid HA. In terms of equilibrium concentrations, it is equal to the equilibrium concentration of A minus, the conjugate base of the acid, times the equilibrium concentration of the hydronium cation, the ionium cation of the solvent here, over the equilibrium concentration of the conjugate acid. If here, instead of HA, we consider the conjugate acid of the solvent, here, hydronium cation, we will have a reaction for which both sides are the same. So we can assume that the acidity constant of the conjugate acid of the solvent, here, acidity constant of hydronium cation for aqueous solutions is equal to 1. We know that acidity constant is a measure of branched acidity. Higher values of acidity constant correspond to higher branched acidities. In addition, higher values of acidity constant correspond to higher values for extent of acid dissociation reaction. So here, for acids stronger than hydronium, acids which have higher branched acidities than that of hydronium cation, the conjugate acid of the solvent. For this acid, we expect the acidity constant to be greater than 1. On the other hand, for acids weaker than hydronium, we expect the acidity constant to be smaller than 1. In aqueous solutions, for acids stronger than hydronium cation, with acidity constant greater than 1, at common concentrations, the acid dissociation reaction is almost complete. Almost all of acids converted to its conjugate base and the conjugate acid of the solvent, and almost none of acid remains in the form of its conjugate acid. For example, for hydroiodic acid, for hydrobromic acid, for hydrochloric acid, which are stronger than the hydronium cation and have acidity constant greater than 1, the acid dissociation reaction is almost complete. And we can consider the following net forward reactions for their acid dissociation. In aqueous solutions, we can assume that these reactions, these acid dissociation reactions, are almost complete. On the other hand, for these acids, which are weaker than the conjugate acid of the solvent and have acidities smaller than 1, the acid dissociation reaction at common concentration is not complete. Not all of the acid is converted to its conjugate base and the conjugate acid of the solvent. A significant part of the acid remains in the form of the conjugate acid at the common concentrations. So for these acids in aqueous solutions, we have to consider the following equilibrium reactions. Here, in fact, also these reactions are equilibrium reactions. But since the equilibrium constant is very great, we can assume them to be almost complete. We can assume them to be net forward reactions. Based on these reactions, we can see that in aqueous solutions, all of these acids are converted to H+, hydronium cation, the conjugate acid of the solvent, and their conjugate bases. So none of the original acid remains, and we don't have these differences between their acidities. What we have is the acidity of the hydronium cation. So at same concentrations, solutions of these acids are equally acidic, have same acidities. We say that the solvent water is a levelling solvent for these acids, and the acidities of these acids are leveled with each other and with the acidity of the conjugate acid of the solvent. On the other hand, this is not the case for these acids, which are weaker than the conjugate acid of the solvent. Here, acid with greater value of acidity constant at same concentration will produce more H+, more hydronium cation. So, solution of acid with a greater Ka acidity constant will be more acidic. Acidity constant of hydrofluoric acid is equal to 10 to the power of minus 3.2, and acidity constant of ammonium cation is equal to the 10 to the power of minus 2.5. Greater acidity constant of hydrofluoric acid means at same concentrations, solutions of hydrofluoric acid will have more H plus than the solutions of ammonium cation. So there will be more acidic, and water differentiates between acidities of these two acids. Water is a differentiating solvent for these two acids. We can represent this graphically. Consider this graph. When acidity increases from bottom to top. Based on this order of Brensted acidities, HI will be at top, then we will have hydrobromic acid, then hydrochloric acid, then hydronium cation, then hydrofluoric acid, and then ammonium cation. In aqueous solutions, acidities of these acids stronger than the conjugate acid of the solvent are leveled with each other and with the acidity of the conjugate acid of the solvent. So, in aqueous solutions, their acidities are leveled with acidity of hydronium cation. We don't have such effect for these acids weaker than the hydronium cation, and water is a differentiating solvent for them. It is common to categorize acids into strong and weak ones. Strong acids are acids like hydroiodic, hydrobromic, hydrochloric, perchloric. The first acid dissociation of sulfuric acid, but not its second acid dissociation, nitric acid, and so on. The weak acids are acids like hydrofluoric, ammonium cation, hydrocyanic, acetic acid, and many more. For strong acids, acid dissociation reaction is almost complete. None of acid remains at equilibrium point. All of it is dissociated. Why this is not the case for weak acids? For weak acid, the acid dissociation reaction at common concentration is not complete. It can't be approximated as complete. And a considerable fraction of acid remains in the form of the conjugate acid. Here we see that strong acids correspond to acids stronger than the conjugate acid of the solvent, and weak acid correspond to acid weaker than the conjugate acid of the solvent. However, it is good to mention, in fact it is important to mention, that this categorization is based on the amount of acid dissociation reaction. For acids whose acid dissociation reaction is complete, they are assumed as strong ones. On the other hand, for acids for which ones that acid dissociation reaction is not complete, they are assumed as weak ones. The fraction of an acid that dissociates in solutions, in addition to the equilibrium constant or acidity constant of the acid, also depends on the concentration of the acid. Higher concentration of concentrations of acid in solutions correspond to smaller fractions of acids which are dissociated. Therefore, here, in addition to acidity constant, concentration is also important. While for the leveling effect of the amphiprotic solvent, we only consider the acidity constants. As a result, at higher concentrations, acids for which acidity constants are not much greater than 1 may not fully dissociate. For example, nitric acid has a pKa of about -1.7. At low and medium concentration, almost all of nitric acid is fully dissociated. So it is a strong acid. But at high concentrations, we can't assume that all of it is dissociated. So at higher concentrations, nitric acid behaves like a weak acid. It doesn't have complete dissociation. On the other hand, weak acids at very low concentrations may behave like strong acids, may have complete acid dissociations. Anyway, for acids like hydroiodic acid, whose acidity constant is much greater than 1, even at higher concentrations, it is possible to assume that the acid dissociation is complete. However, at very high concentrations, other effects may be present in solutions, and the discussion might be different. Another important point here is the fact that for strong acids, we can consider base dissociation reaction for their conjugate bases, while for weak acids, we can't do so. For example, hydroiodic acid is a strong acid. This means all of it is dissociated. So, all of hydroiodic acid is instantaneously converted to its conjugate base and hydronium cation, and none of it remains. So, no reaction can produce it, and the base dissociation reaction of the conjugate base of hydroiodic acid, which produces hydroiodic acid, has no meaning. So, for example, we don't consider reactions such as this in aqueous solutions. Since in aqueous solutions, hydroiodic acid is a strong acid, all of it is dissociated, so we can't have it in aqueous solutions. Therefore, the base dissociation reaction of its conjugate base, which produces the conjugate acid, has no meaning. On the other hand, we can consider base dissociation reaction for the conjugate base of weak acids. For example, we can consider this reaction. This is the base dissociation reaction of the fluoride anion in aqueous solutions. The fluoride anion is the conjugate base of the hydrofluoric acid, a weak acid in aqueous solutions. We can consider a similar discussion for bases. Let's consider an example. In aqueous solutions, we have the following order of Brand-Sted basicities. Brand-Sted basicity of metanide anion is greater than that of the amide anion. It is greater than that of the hydroxide anion, the conjugate base of the water. It's levelleing anion. It is greater than the cyanide anion, and it is greater than fluoride anion. For bases like metanide and amide, whose Brand-Sted basicity is greater than that of the conjugate base of the solvent water makes their basicities appear the same. Aqueous solutions of these Brand-Sted bases at same concentrations will have equal basicities. On the other hand, water is a levelleing solvent for these bases. On the other hand, this is not the case for these bases, which are weaker than the conjugate base of the solvent. They will not appear to have same bases in aqueous solutions. Aqueous solutions of these bases at same concentration will have different basicities. Here also, consideration of base dissociation reaction and basicity constants are very useful. For the Brand-Sted base A- in aqueous solution, the base dissociation reaction is as follows. For this reaction, the basicity constant of the Brand-Sted base A- in terms of equilibrium concentration is equal to the equilibrium concentration of conjugate acid times the equilibrium concentration of the hydroxide anion over the equilibrium concentration of the conjugate base. If here, instead of A-, we consider hydroxide anion, we will have a reaction for which both sides are the same. So, the basicity constant of the conjugate base of the solvent in aqueous solutions can be assumed to be equal to 1. We know that basicity constant is a measure of Brand-Sted basicity. Higher values of basicity constants correspond to higher Brand-Sted basicities. Also, higher values of basicity constants correspond to greater extent of reactions, greater extent of base dissociation reaction. Therefore, we can say that for bases stronger than hydroxide anion, the conjugate base of the solvent water in aqueous solutions, basicity constant is greater than 1, while for bases weaker than hydroxide anion, the basicity constant is smaller than 1. In aqueous solutions, for bases which are stronger than the conjugate base of the solvent and have basicity constant greater than 1, at common concentration, the base dissociation reaction is almost complete. Almost all of the base is converted to its conjugate acid and lyate anion or conjugate base of the solvent. Almost none of the original base remains in the form of the conjugate base. For example, for these bases which are stronger than the lyate anion of water, in aqueous solutions, base dissociation reactions are almost complete and can be represented by the following net forward reactions. On the other hand, for bases which are weaker than the conjugate base of the solvent and have basic constants smaller than 1 in aqueous solutions at common concentrations, base dissociation reactions are not complete, can't be assumed or approximated to be complete. A significant fraction of the original base remains in the form of the conjugate base, and not all of it is converted to the conjugate acid and the lyate anion of the solvent. So here, for example, for these branched bases which are weaker than the conjugate base of the solvent, we can consider the following equilibrium reactions as the base dissociation reactions. In fact, these reactions are also equilibrium reactions, but their equilibrium constants are so great that we can assume them to be almost complete. We can consider them as net forward reactions, but we can't do so for these reactions. For these bases stronger than the conjugate base of the solvent, base dissociation reactions are complete. All of them are converted to the conjugate acid and the hydroxide anion. The only base present to any significant extent in their solutions is the hydroxide anion. At same concentrations, they will have same basicities. Water is a levelling solvent for these bases. Their basicities are leveled with each other and with the hydroxide anion. On the other hand, this is not the case with these bases, which are weaker than the conjugate base of the solvent. Here, the stronger base has greater basicity constant. For cyanide, Kb is equal to the 10 to the power of minus 4.979 at 25 degrees Celsius, while for fluoride anion, Kb is equal to the 10 to the power of minus 10.8. For these bases, weaker than the conjugate base of the solvent, base with greater value of basicity constant at same concentrations will produce more hydroxide anion, so solutions of the base with greater value of Kb will be more basic. It will have more of this base. So here we see that water is a differentiating solvent for these bases. It differentiates their basicities. In aqueous solutions, Cyanide is stronger than fluoride anion. We can represent this graphically like this. Let's assume that the Brensted basicity increases from bottom to top. Metonite anion will have the highest Brensted basicity here. Then we will have amide anion. Then hydroxide anion, the liate anion of the solvent, the conjugate base of the solvent. Then cyanide anion, and then fluoride anion. Water is a leveling solvent for these bases, which are stronger than the conjugate base of the solvent. Their basicity is leveled with each other and with the conjugate base of the solvent. But we don't have such effect for these bases. Water is a differentiating solvent for these bases, which are weaker than the conjugate base of the solvent. Like acids, we can also categorize bases into strong and weak ones. For strong bases, base dissociation reaction is complete, while for weak bases, it is not so. Strong bases such as sodium hydroxide, potassium hydroxide, barium hydroxide, amide anion, metonite anion, and so on. Weak bases such as cyanide, fluoride, acetate anion, and so on. Again here, the fraction of the base that dissociates, in addition to the value of the basicity constant, also depends on the concentration of the base. So, bases which behave like strong bases, bases which fully dissociate at low concentrations, may not behave as strong bases at high concentrations. We assume that for strong bases, base dissociation reaction is almost complete. So, all of the strong base is instantaneously converted to its conjugate acid and the liate anion of the solvent. So reactions which produce the base are meaningless. Therefore, for strong bases, we don't consider acid dissociation reaction for their conjugate acids. But for weak bases, we can consider acid dissociation reactions for their conjugate acids. So, for example, metonite is a strong base. Therefore, acid dissociation reaction of its conjugate acid, this reaction is meaningless. While fluoride anion is a weak base, so acid dissociation reaction of its conjugate acid can be considered. These examples were for aqueous solutions. We can discuss similarly for non-aqueous solutions of other amphiprotic solvents. This is the end of this online tutorial. I hope you find it useful.